Students, in the last class, we have to solve some problems on subgroups, and then we start the definition of cyclic group and solve some examples of a cyclic groups. We stop last class with these examples that the group of U7 is a cyclic group with the generator 3, and then we have to show that 3 and 5 are the generator, because you know that if a group element G is a generator, then its inverse is also the generator of this cyclic group. So in this group 3 and 5 are the inverse of each other. So 3 is a generator and then 5 is also the generator. But we show that 2 and 4 are not a generator of a group, they cannot generate the whole group. So that means only 3 and 5 are the generator of a U7. Then we have to taking the another example. We take a multiplicative group like this 1, 2, 4, 1 by 2, 1 by 4, 1 by 8 and so on, and then we can easily check that the 2 and 1 by 2 are the generators of a this group. No other elements are the generators of this group. So now we have to continue for this cyclic group. So previously we have to solve some examples showing that are cyclic. Now I just today the first example we have to check that is not a we have to take this U8, and then clearly U8 is not a cyclic. So the elements of a U8 is equal to 1, 3, 5, 7, because 1, 3, 5, 7 are relatively prime to 8. So this is clearly under multiplication is form a group. Now if we take a see the what is the generator of this is 1 is clearly is not the generator of this group, because 1 to the power 1 is every time we have to getting the 1. And then if you have to try to 3, we have to take a 3 to the power 0 is equal to 1, 3 to the power 1 is equal to 3, then we have a 3 square is equal to, you have again we have to getting 1. So this means is a repetition start. So this means is generated 3 is equal to, we have a 1 and 3. So if this is generated by 3, we have only is equal to 1 and 3. Let us try for another element of 5. So you have to take a 5 to the power 0, 1, 5 to the power 1 is equal to 5, then 5 to the power 2 is equal to, we have again is equal to 1. So in this case, if we have generated by 5 is equal to, we have a 1 and 5, and then similarly 7 to the power 0 is equal to 1, and then 7 to the power 1 is equal to 7, and 7 to the power 2 is equal to again is equal. So if we have generated by 7, we have only is equal to 1 and 7. So in this group we cannot find any element which can generate a whole the set. So that is 1 generated by 1 is equal to 1, 3 is by 1 3, 5 1 5, and 7 is 1 7. So clearly this U8 is not a cyclic group. We cannot find any G which can generate of the element of a U8 which can generate the whole the group elements of this generated by this. Another example we have to just discuss is not a cyclic. We have a set of a rational number under addition is also not a cyclic. Now we have to know that the set of rational number, let if possible Q is generated by Q, where Q is equal to m by n, where m and n are the integers, such that n should be not equal to 0. So we assuming that if Q is a cyclic, so if means is a cycle is generated by some element Q, and Q can be written in the form of m by n, where m and n are the integers, and n not equal to 0. Then for each x belongs to K, then x can be written in the form of a k x is equal to k times for some integer k times of a Q. And in particular for x is equal to, if we take a 1 by 5 n belongs to Q, we have 1 by 5 n is equal to, we have to take LQ, where some integers L, and this is implies that 1 upon 5 n is equal to Q is equal to, we have to take m by n. So L m I n, and then we have to imply that 1 by 3 is 1 by yeah, this is 1 by 5 is equal to I of m. I or m are the integer, so im is the element of a z. So this is clearly this 1 by 5 is an integer. This is impossible. So we have to say q under addition is not a cyclic. So this should be is equal to, we have a 5. This is 5 in place of a 3. We have a 5, 1 by 3 n is equal to L by n. So this we have to clearly we have to just say that in this form. So 1 by 5 is an integer. So this is impossible. So q under addition is clearly this q under addition is not a cyclic group. So now we have to prove a result which say that every cyclic group is abelian but converse does not hold. So we show that every cyclic group is abelian. So we just take first, let G be a cyclic group. If it is cyclic group, then it is a generator. Let G be the generator of this G. Then this generated by G to the power n, and this is should be is equal to, we have a some n is the element of a Z. So G is generated by G to the power n, and then n is belongs to the set of this. So clearly this is not a, this is n. So n belongs to the Z. Then we have to clearly write that let x and y be any two elements of a G, and x and y be any two elements of a G. There exist integers r and s. X to the power x is can be written as a G to the power n. R and y can be written as a G to the power s, because x and y are the element, and this is the cyclic group. So x is the sum, G is a generator. So if G is a generator, then x is some power of a G. Y is a generator, then y is also just some power of a G. Then x and y is equal to can be written as x G to the power r, G to the power s, and G to the power r plus s, where r and s integer. So this sum of integers is clearly we have to just say that is a commutative. So this can be written as a G to the power s plus r, and then again by the property of this we can write G to the power s into G to the power r, and this is equal to y of x. So we clearly show that if we take any two elements of a G, then we show that xy is equal to yx. So every cyclic group is abelian. Now we have to show that converse is not true. We have a abelian group but not a cyclic. One of the example, just previous example you have to see, q under addition we have to show that is a is not a cyclic, but q under addition is an abelian group. So another we have to just previously we show that this U8 also, there's a previous two examples. One is we have to just say that rational number under addition is abelian clearly, is not a cyclic, and also U8 is we can U8 we can easily check this is a abelian under multiplication modulo 8, 1, 3, 5, 7, and then 1, 3, 5, 7 by the table, then is equal to 1, 3, 5, 7, 3, 5, 7, then you have 1. Then similarly we have to complete all the elements of there. So this is clearly this is a abelian group. If we take a 3 into 5 is equal to same as a 5 into 3, and also 3 into 7 is the same as a 7 into 3. So all the elements, this means clearly we say that this is a any two elements taken is a abelian, but clearly this is not a cyclic group. We cannot find any element in this U8 which generate the whole set of this group is there. So next we have to just another theorem, we have to show that let G be an element of a group G, and then H can be written in the form of a G to the power n, and belongs to Z. Then H is a subgroup of a G, and furthermore we show that this H is the smallest subgroup of a G containing H, and then finally we have to show that this H is abelian. So we take a G and G be an element of the group, then H generated by G means if H is generated by we take a subgroup which is generated by H is generated by this, then this H is a subgroup of a group G, and we have also show that this H is the smallest subgroup of G that contains the G, and then finally we show that this H is a abelian. First we show that H is a subgroup. So clearly G to the power 0 we can write is equal to G, so is equal to identity. So identity is the element of H, and H is a clearly is a non-empty. So E can be written as E to the power 0. So E is the element of H. This is a, so clearly H is a non-empty. Now we have to take any two elements of this set and then show that the X and Y are the element of H. Then we have to show that XY inverse also belongs to the H, or XY element of H, then XY is the element of H, and X is the element of H, X inverse is also the element by the criteria of a subgroup. So suppose X and Y are the element of H. If X and Y are the element of H, because this X is generated by H, H is generated by G, so this X can be written as a G to the power R. Y is the element of H, then Y is also generated by the G, so some G to the power S. For some R and S are the integers. And if we write X and Y, XY can be written as a G to the power R, G to the power R, and G to the power R plus S, and G to the power R plus S is belongs to Z. So clearly we can say that again is integer. So XY can also written in the form of a powers of a some G. So this means XY can generated by G. So hence XY is also the element of a H is there. Now we have to show that the X inverse is also the element of H. So if X is the element of a H, means X can be written in the form of a G to the power R, and moreover X inverse can be written as a GR. So X is equal to, we have a G to the power R, then X inverse can be written in the form of a GR inverse, and then by the exponential property we can say that this is GR, so G to the power minus R, and then R is an integer, so minus R is also belongs to this is Z. So this we can say that this generated by, again the G can be written as some powers of integers. So X inverse can be generated by G to the power some integers. So we can say that this is the element of a H. So X inverse is also the element of H. So we use all the three properties of a subgroup is hold here. We show that H is H is a non-empty, X is closed, and inverse is also exists there. So we can say that this H is generated by G is clearly is a subgroup. Now we have to show that this subgroup is the smallest subgroup of a G containing H. So we shall now prove that H is the smallest subgroup of G containing G belongs to H. So let K be a subgroup of a G contains G. Since K is a subgroup, so it must contain all powers of a G, that is G to the power n is the element of a K, for all n is the element of a Z. And is containing, this means H is containing into the clearly K. And thus H is the smallest subgroup of a G is containing G is there. So if we take any another subgroup K and of G that's contain G, and K is a subgroup, so it must be contains all powers of a G, and that means G to the power n is belongs to K, and H is the G is the element of H, and we have to show that G some powers of a also K. So this means H is a subset of a K, and H is the smallest subgroup of G containing into containing G is there. Now finally we have to show that this H is a abelian. So we take any two element X and Y is the element of H. So we take X and Y is the element of H, and then if H, then X can be written as a G to the power R, and Y can be written as a G to the power S, and then we have a X, Y can be written as a G to the power R, G to the power S, G to the power R plus S, where R and S are the some integers. And if R plus S are the R and S are the integer, then R plus S is also integer, and if r plus s is also integer, then r plus s is commutative under the addition. So this can be written as g of s plus r, and this can be written as g to the power s, g to the power r, and this is nothing but is equal to y into x is there. So we finally we show that the if x and y is all the element of a h, then xy is also yx. So this means this h is a commutative group is also. This satisfies the commutative conditions. So this means we can say that this h is an abelian group. So this h is an abelian. Now we have to define the, by this we can say that you can, by the previous theorem we just show that this any G be an element of a group G, and right H can be as a generated by a element of this G, and then this is satisfy the condition is satisfy this H is a group. So H is a subgroup. This means we can define let G be a group and G is the element of H. Then the cyclic subgroup generated by G is the set of all powers of a G, and we write G to the power n. Of course, the group G is cyclic if and only if there exists an element G belongs to G and G is generated by G. So if we can by this, so now we have to solve by the and this result. Every subgroup of a cyclic group is a cyclic. So we just said that if we take any cyclic group and take a subgroup of this is also cyclic. So we take a let we proving this theorem by using the division algorithm and principle of a well ordering principle. So we suppose G is equal to G to the power k is some integer, is a cyclic group, and let H be a subgroup of a G. We take this G is a cyclic group and we take a H is a subgroup of a J. If H is equal to identity, then trivially H is a cyclic. So result is proved. Now that means we have to, this is trivially, so we assume that H is not a identity. That means if not is identity means there is some other element as to some power of a G which is the element of a H, and except G to the power k is not equal to identity. So we have to assuming that H is not the identity element. After identity there is some other elements also. So some other powers of G is belongs to the H, and clearly G to the power k not the identity. So now since H is a subgroup, so we can say that H is a subgroup, then G to the power minus k can be written as a G to the power k inverse, and G to the power k is the element of H, then every element, because H is a subgroup, then every inverse of H is also belongs to the H. So if G to the power k inverse of G to the power k is also H, and G to the power k inverse can be written G to the power minus k, so this is also the element. So this means we can say that this is G to the power minus k is also the element of a H is there. So this means therefore since k or minus k is positive, so H contains a positive power of a G not equal to identity. So we can say simply that then m be the smallest positive integer such that G to the power m belongs to the H. Then certainly all powers of G to the power m are also in H, because this m is the smallest, and this is the all certainly all powers of G to the power m is also into H, generated by generator of G to the power m containing into H is by the clearly trivially. Because all powers of G to the also belong to H, this means G to the power m is the element of H, and this is a small m where m is the smallest positive integer. So we claim that the inclusion is equality. We have to just claim in place of this G to the power m is equal to is an equality hold. In place of inclusion, we have to show that this is equality is there. So to see this, let G to the power k be any element of H, recalling that all the elements of a G and hence H are all powers of a G, since G is a cyclic. So by the division algorithm, we can write k can be written in the form of a qm plus r, and where r lies between 0 and m. But g to the power k can be written as a g to the power qm plus r, and this can be written as g to the power qm g to the power r, and then we have to g to the power m to the power q, and we can say that into the r. So g to the power r, from here we can write g to the power m to the power q is inverse. So this means g to the power r can be written in the form of a g to the power m to the power minus q into g to the power k. And now you just see the g to the power m is the element of a h, and g to the power k is also be an element of h, and then it to power inverse is also, though this is whole element, this is whole that belongs to the h. If whole belongs to the h, that means g to the power r is also the member of h. If g to the power is also the member of h, and since m is the smallest positive integer with g to the power m is equal to belongs to the h, and r lies between g to the power this means this follows that only possibility is we have a r is equal to 0. If r is equal to 0, then you can see g to the power k, we can say this is written in the form of a g to the power by r is equal to 0. The g to the power k can be written in the form of a g to the power m to the power q, and g to the power m to the power some power of this clearly generated by g to the power m is there. So hence we show that firstly we show that this g to the power m is contained into the h. Now by this g to the power k is the element of h, and this is also belongs to the this. So this means we can say that h is containing into this. So by these two we can say that h is equal to g to the power m. So we have to show that this is clearly is a result is hold. Every subgroup of a cyclic group is a cyclic group is there. Now this example we have to consider a group of addition modulo 4 under modulo 4. Then you can see the element of a Z4 is 0, 1, 2, 3. If A is the element of a Z4, then generated by A is equal to NA, N is belongs to the Z4. This is. So let us find the cyclic subgroup generated by the non-zero elements of a Z4. We have a first element is a, we have to just write as a 1. If it is generated by 1, clearly, so this can be written as a n under addition modulo 4, 1, such that n is the element of a integer Z4. So we just say that if you have n is equal to z, so we can just say this is n is a z, not a Z4. So we can write n under addition modulo 1. So we can write n, we have to take a n is equal to 1, n is equal to 0, and so on. So n is equal to 1 and 4, so we have to getting a 0, 1, and so on like this. We have to getting the 0, 1, 2, 3, again 0, 1, and then we have to just under addition modulo 4, we have to getting into this form. So this is only z, not Z4. So 0, 1, 2, 3, and using the congruent modulo is equal to this. This is 1 is generated by whole the group. This we know that 1 is the generator of a Zn, so clearly 1 is the generator of. Now we take a 2 and then n addition modulo 4 2. If n is the element of a z, then we clearly if we take n is equal to, we take a z is equal to 0. So 2 n is equal to 2, then we have a clearly 0, and then we have to 0, 2, 0, 2, 0, 2, then we have a only 0. So this clearly 2 is not the generator of a this group. Now we have to take a 3, and then clearly we have a 3 is equal to n plus addition modulo 3, and then 0, 3, 2, 1, and so on, again 0, 3, 2, 1, 30. So we have a 0, 1, 2, 3, and that is equal to Z4. So in this Z4 we have a under addition modulo 4, we have a 2 generators, 1 is a generator and 3 is a generator. And now you know that because 1 and 3 are the generator, 1 and 3 are the inverse of each other, we show that if 1 is a generator and G is a generator, then G inverse is also the generator of a cis cyclic group. So this clearly we show that these two example we have to show that again if we have a point generator of a non-zero elements of a, because 0 is not a generator of this group, we have to adding a 0 any times we are getting the 0 in this form. So I have to stop today's lectures here with this example, and we have to try to continue with the next class with some more properties of a cyclic group and some more examples and future problems of a cyclic group. So I have to stop here today and we have to continue from next class. Thank you.